Continuing on with 2.1.2, example 3. All right, so this one's a little different. We have something going on the left side. Again, not really a whole lot going on here on the right, just two terms, 6x and 14. But over here we got, what you should obviously recognize, I hope, as the distributive property. So we need to take this 2 and multiply it through both parts. Okay, what's going to happen here is you're going to get 6x plus 2 equals 6x plus 14. Again, I use the distributive property there. Now, I can already tell this is going to give me a very interesting scenario. So I want to get my x's on the same side. So I'm already thinking, okay, well, I need to move it. So let's move the one on the right to the left. So I subtract 6x on both sides. And what happens, as you'll see, 6x minus 6x goes to 0. And on the left side, 6x minus 6x also goes to 0, leaving me with this. Now, what do you know about that? I'm hoping you're going to say that those two numbers aren't equal, Mr. Reynolds, and they're not. Anytime you solve an equation that has variables on both sides and you get this, you get a number is not equal to some other number. That's called no solution. I'm hoping you remember that from 8th grade. But if not, we're going to go back through it real quick. When you get x equals a number, that's a potential solution, right? But when you get that all the x's have disappeared and you have this, that basically means that there's no answer. In other words, if you were to graph these two lines, they would never intersect, right? They would never cross each other. As a matter of fact, if we separated this out, I'm going to do this just to kind of give you an idea here. If we were to do y equaled 2 times 3x plus 1, and then y equaled 6x plus 14, if we separated that out into two separate equations, and then I simplified this first one, y equals 6x plus 2, and then I compare the two, what you should know is that they have what? That right there, the 6. That's y equals mx plus b, and m is your slope. So for both of these, they have a slope of m. And they have different y-intercepts, which tells me something about those two lines when you graph them. It means that those two lines are parallel. Okay, those two lines are parallel. That means they never cross. They never intersect. They're like railroad tracks. They just run right next to each other forever and ever and ever. Okay, which means they can't possibly have, there cannot be a point that satisfies both of them. Okay, all right, good deal. Moving on to the next one. Similar setup, very similar setup here. We have, two terms on the right side, and then we have distributive property on the left side. So I'm going to go ahead and clean up that distributive property, and I get 12x plus 6 equals 12x plus 6. Now, some of you at this point will probably already go, ooh, I know what's going on here, but let's go ahead and just work it down. If you were to get the x's on the same side, like I tell you to, that's what I always try to do first, is the variables first. What you notice here is you end up with 6 equals 6. This time, the variables did not, they did cancel out, but they did not give us an equation that is not true. They gave us a number equals itself. Okay? And this is another special case, another special solution that has infinitely many solutions. Okay? Or you could say all real numbers will satisfy this. Basically, what we're saying here is if we were to split this out into two equations, and y equals 12x plus 6, what we're actually saying here is that these two lines are what? They are identical. They are on top of each other, right? It's literally the same line graphically. So everything that is a solution to one is a solution to the other, right? You can plug in any number for x, and it will work for both of them. We'll get into all real number stuff later. For now, we're going to focus on this. Infinitely many solutions, IMS. Any real number that you could plug in for x on both sides is going to work, right? It's going to give you the same thing because they are literally identical to each other. All right? So that's what we're going to focus on here, and that's what happens when this situation occurs. When you get a true statement at the end, but all the variables still went away. Okay? All right, one last one. I'm going to go through it fairly quickly. Y'all seen these before? This is just solving the literal equation. This is review almost, but it's still following those properties, right? So I have multiplication. I have 1/2 times b1 plus b2 times h, right? And that equals a. I want to get rid of, the stuff, right? So how do I undo multiplication? Well, I divide, but, fractions. We don't divide by fractions. We multiply by their reciprocal. So what happens here is you get 2/1 times 1/2, which goes to 1, which means it can't cancel each other out. And now I have 2a equals b1 plus b2 times h. Now I have some multiplication to undo because I can't undo those parentheses yet. So I divide by h. And that leaves me with 2a over h equals b1 plus b2. And then the last thing I need to do is the subtraction property to undo this addition of b2. So minus b2. But I do it on both sides. So minus b2. Which means I'm doing this whole thing, this whole part, minus b2. Okay, so what does that look like? Well, it's going to be 2a over h minus b2 equals b1. And there's nothing else I can do with that. The goal here was to solve for b1, which I have done. All right, so there's your last 3 examples for 2.1.2. Go ahead and be working on the Walsh questions for 2.1.1 and 2.1.2. Okay, focus on those tasks first because those are the ones that are worth the most points. Those assignments are. So go ahead and start your focus there right after you watch these videos and go through the problem tests. All right, good luck. Ask me if you have questions, guys.